Hello and welcome to this new video series about basic topology, where we will discuss notions like open, closed and compact. Indeed, here I want to cover a lot of stuff from topology that helps you in analysis. Therefore, I will assume that you have the essential knowledge of my course about real analysis. As always, you don't need all the details there, but for example, the knowledge of a continuous function on the real numbers would be important. Moreover, also the generalization to n dimensions in the multivariable calculus course is good to know here. In fact, in this basic topology course here, we will leave the concrete space Rn and we will work in a really abstract setting. And I say basic because we will deal with a lot of fundamentals in topology, and I also want to create a more advanced course as well. And as a regular viewer of the channel, you might already know that we already have covered some topological definitions in some other courses. For example, in the manifold series and the functional analysis series, we already needed general topological spaces. Therefore, you definitely might see some overlap here at the beginning of the new series. Moreover, as already promised, in the end we will also be able to continue with so-called algebraic topology. This is something for the future, and I will put this into a different video course altogether. Obviously, it's not so clear where we can make the cut between the two topics, but first I want to cover everything in topology which we can use in analysis. And this comes down to the basic definitions and a lot of discussions in so-called Hausdorff spaces. So a so-called topological space here is the general notion, and a Hausdorff space is a special case of it. And together with a notion we call locally compact, we still cover a lot of properties that we have in our analysis context. So in fact, this is the generalization as we want to have it. And in order to see that, we can immediately start with an ordinary metric space. This one is just an arbitrary set X together with a metric D. And the metric D is just there to measure the distance between 2 points in X. And therefore it has to be a map defined on the Cartesian product that goes into the non-negative real numbers. Indeed, this is how we want to measure a distance. It has to be a non-negative real number. And moreover, we also want to satisfy 3 defining properties for this map. First, it has to be a positive definite map, which means that the distance 0 is only allowed if the 2 points coincide. This is quite natural. This is what we want to have for a well-defined distance measure. And in a similar way, we also want that this map is symmetric, so it does not matter if we exchange the 2 points in it. So d of xy is equal to d of yx for every x and y in X. And finally, we also want to have the triangle inequality, which means if we measure over a detour, the distance only gets larger. So in the formula, this means if we have x to z, then this one cannot be bigger if we add up the distance x to y and y to z. So we just put y in the middle, and there you can see it's good that we work with real numbers because we have an inequality and we have the addition in it. And it's simply called triangle inequality because if we visualize it, the 3 points form a triangle. And now you know with this metric the connection from x to z is definitely smaller than these 2 distances added. And as before, this has to hold for any point x, y and z in our set X. And there you might already know, this set together with a metric is called a metric space XD. Indeed, usually you see that written as a pair. And now as a general rule, in topology, we just generalize everything we know in metric spaces. Roughly speaking, we will forget about the explicit distance we have between points and just talk about closeness. This means in a picture everything is much more flexible because distances can change as we want, and it's just about neighborhoods of points. And there are different possibilities to put it into a precise definition, and one common one is just to use so-called open sets. And this is quite nice because open sets already exist in a metric space. For example, you might know the open epsilon ball around a point X. This is quite simple because you just take all the points y into the set that have a distance less than epsilon. And therefore you just say you have a ball with radius epsilon. And in the formula this would mean that we have dxy less than epsilon. In short, we just call it an open epsilon ball, but if you want to be precise, you can say it's the open ball of radius epsilon centered at x. And there you should see that this definition is quite important because it tells us that all the neighboring points around x are included in this open ball. And therefore the whole definition only makes sense if we choose our epsilon greater than 0. And now, as you might know, these epsilon balls are used to define the notion open in metric spaces. This means we just take a metric space XD and then we look at a subset A in X. And now for any subset A, we can decide if it's open or not. And here, please never forget, this notion open is always with respect to the given metric space. And as a rough idea, if you visualize it, then it means that the boundary is not included in the set A. The meaning of that is that you can just take any point x in the set A, and then in every direction you find neighboring points for x that lie completely in A. In other words, a whole epsilon ball around x lies completely in A. And this should work no matter which point x we choose. Indeed, in the picture you already see, the closer we are at the boundary, the smaller the epsilon has to be. So the epsilon can definitely depend on x, and it's only important that we can find a positive one. So this is the general definition of an open set in a metric space, and with that we can also show that the so-called open balls are also open sets with this definition. This is not so hard, this is essentially just putting smaller balls into a bigger one. Okay, and now the idea we have for topology is to use this notion open without using open balls at all. And this is possible by just looking at the properties we have for open sets in metric spaces. So first of all, it's not hard at all to find open subsets in a metric space. Simply because the definition is trivially fulfilled for the empty set and X itself. And now imagine that we have two different open sets A and B. Then we could look at the intersection of both sets and let's assume it's not empty. This means we can look at a point X they have in common. And with the assumption that A and B are open, we know that we have an epsilon ball in A and one in B around X. And now of course the correct picture would be that we have an overlap because the 2 points X are actually the same thing. And then since both balls are centered at the same point, we know that one of them has to be the smaller one. Which also implies that the smaller one completely lies in the intersection between A and B. And since this works for any point in the intersection, by definition the intersection is also an open set. And at this point it should not surprise you that we can do a similar thing for the union. And you might already see it in the picture that for a union any of the two epsilon balls would work. And for that reason we could actually consider any collection of open sets. Therefore for an arbitrary index set I, we can look at the union. And this one still satisfies the condition with the epsilon ball. This is quite simple because in contrast to the intersection, a union will not lose points. And now it turns out that these properties are already sufficient to describe the whole collection of open sets in a metric space. And this is quite nice because in these properties we don't need to measure distances at all. And for that reason, this can be the starting point to describe a topology where we don't have a metric given. And in fact, this is exactly the generalization we want to do in this video course. So you can already remember, this will be our foundation where everything is based on. So in other words, we will transform these properties into a definition. However, this is something for the next video, so I really hope I meet you there again and have a nice day. Bye bye.